Hi there, happy Saturday. I'm going to introduce you a very nice experiments going on at Chemical Dynamics Spin Line 9.0.2 at ALS synchrotron, which is at LBNL Berkeley. So in this experiment, we are trying to create the condition of the early solar system where we are dissociating CO in the presence of hydrogen. That is known to be one of the processes in early solar nebula, and that changed the isotopic composition of some of the abundant gas species like oxygen, carbon, and so on. So in this experiment, you can see the whole chamber is cooled down by liquid nitrogen, and you can see the temperature, which is reading right now 82.5 K. So this is kind of very far off from the sun in the early stage, something like few tenths of AU away, and we are flowing the gas of CO and hydrogen mixture through this port, and it flows through the chamber all the way and comes out at this end here, and it follows through 1, 2, 3 normal trap frozen with LN2, and another trap. This is filled with molecular sieve, and finally it goes out to the pump. So the basic idea is the CO will photodissociate and form C and O atom, and in presence of hydrogen, the reaction will take place to form CO2, methane, and water mainly, and some may not happen inside the chamber. So during its exit, some reaction may also happen. So while all these are happening, we will trap CO2 and H2O in this cold trap, but some may slip through. That's why we have all these three traps filled with liquid nitrogen, so we don't miss anything. But when you produce methane, so when we produce methane will not be trapped in this liquid nitrogen trap. We need another agent called molecular sieve, which is there in this trap, and this is kind of temperature controlled. So we can change the variac setting and make a temperature of this. So right now, methane and CO both are getting frozen here in this trap, and once the experiments are done, we'll collect the condensables in this chamber, in these three traps, by elevating the temperature of this reaction chamber to close to room temperature. So everything will come and freeze back here, and once they are there, we'll finally collect in the sample tube, which are condensable, maybe CO2 and water. We'll take the CO2 and water at UCSD, and we'll separate them out cryogenically, and we'll do isotopic analysis of carbon and oxygen on these two species. When you measure CO2 of that when we measure oxygen isotope of that CO2, it gives the photodissociated oxygen, but should not give the photodissociated carbon component, because CO2 is forming by combining with O atom, which is photodissociation product with the bulk gas CO. So if you measure the 13:12 ratio of that CO2, you will not get the photodissociation effect in carbon. That's why we are trying to do methane, because this photodissociated C will combine with hydrogen and methane. So in this trap where we see the CO and CH4 are both frozen, we'll try to separate them out. We'll do some here by changing the temperature, because liquid nitrogen traps methane at minus 155 degrees centigrade. At that temperature, CO doesn't freeze, but that separation in this trap may not be very perfect. So what we will do, we'll take this one, do a GC separation, and after that we'll throw out the CO because that doesn't carry any information. We'll collect methane and we will do a pyrolysis in presence of cuprous oxide at 800 degrees centigrade for 8 hours and produce CO2 and measure the CO2 for carbon isotopic analysis. So a lot of things are going on in this here, the basic physical chemistry, and we have shown that CO2 photodissociation produces large isotope effect. We are hoping that the CO photodissociation will also produce a large isotope effect in carbon isotopes, and let's see what happens. Thank you very much for your attention, and again, happy weekend.